I am become death, destroyer of worlds. These words, spoken by J. Robert Oppenheimer as he witnessed the first nuclear explosion, would haunt him for the rest of his life. But what drove a brilliant physicist to create the most destructive weapon in human history? And what price did he pay for unleashing the power of the sun itself? When Oppenheimer arrived at the desolate mesa of Los Alamos in 1943, he carried with him not just the weight of scientific ambition, but the desperate urgency of a world at war. The Manhattan Project wasn't born from conquest. It was born from fear. Fear that Nazi Germany would develop the atomic bomb first. But transforming theoretical physics into apocalyptic reality would prove far more challenging than anyone imagined. Oppenheimer, the chain-smoking intellectual who quoted Sanskrit and read French poetry, suddenly found himself managing the most complex scientific endeavor in human history. Chapter 1. The Impossible Physics. The science seems simple enough on paper. Split the atom, release enormous energy, build a bomb. But the reality was a nightmare of variables, calculations, and deadly materials that could kill you before you even knew you'd made a mistake. First, they needed uranium-235, but separating it from uranium-238 was like trying to separate identical twins using only their weight difference. Out of every 1,000 uranium atoms, only 7 were the type they needed. The electromagnetic separation plants at Oak Ridge consumed more electricity than entire cities, yet produced uranium-235 at the rate of a few grams per day. The Calatrons, massive electromagnetic machines weighing 3,000 tons each, operated day and night, requiring silver borrowed from the U.S. Treasury because copper was too scarce for wartime use. The operators, mostly young women recruited from Tennessee high schools, had no idea they were enriching uranium for atomic weapons. They were simply told to keep certain dials within specific ranges, watching green lines dance across oscilloscope screens. Many of these women became so skilled that they could detect the slightest variations in the separation process, often outperforming the PhD physicists who had designed the machines. Meanwhile, the gaseous diffusion process at Oak Ridge represented another monumental challenge. Uranium hexafluoride gas had to pass through thousands of barriers with microscopic holes, each hole smaller than a virus. The gas was so corrosive it ate through most materials, forcing engineers to develop entirely new alloys and sealing compounds. The diffusion plant stretched for miles, requiring its own power grid and cooling system. Then came the plutonium pathway, equally treacherous. Creating plutonium required building nuclear reactors that had never existed before. The first reactor at Hanford nearly suffered a meltdown when xenon poisoning caused an unexpected shutdown. Engineers worked around the clock, not knowing if they were one miscalculation away from a catastrophic explosion. The Hanford reactors themselves were engineering marvels born from desperation. Each reactor contained 2004 aluminum tubes filled with uranium slugs, cooled by Columbia River water pumped at 75,000 gallons per minute. The radiation levels were so intense, the fuel rods could only be changed using remote-controlled equipment. Workers operated behind thick concrete walls, manipulating robotic arms through periscopes, never directly seeing the materials they handled. But the plutonium produced was not pure. Scientists discovered that plutonium reactor contained Pu-40, which spontaneously fissioned at an unpredictable rate. This contamination meant the gun-type design used for uranium would never work with plutonium. The material would begin reacting before achieving optimal compression, resulting in a weak fizzle instead of a devastating explosion. But even with fissile material, the engineering challenges multiplied. How do you compress uranium to the precise density needed for a chain reaction? How fast must the compression occur? Too slow, and the reaction fizzles. Too fast, and the bomb destroys itself before reaching full potential. Chapter 2. The Laboratory of Nightmares. Los Alamos was a city of brilliant minds living on the edge of disaster. Scientists handled plutonium with their bare hands, not fully understanding its lethality. The metal felt warm to the touch, a sinister heat generated by radioactive decay. Louis Slotin, a young Canadian physicist, performed what colleagues called tickling the dragon's tail, manually bringing pieces of fissile material to the brink of criticality using just a screwdriver to separate hemispheres of plutonium. His hands would literally feel the heat of approaching chain reaction, the air itself becoming ionized as atoms began splitting. Slotin's experiments were terrifyingly precise. He would slowly lower one hemisphere of plutonium toward another, watching neutron counters and feeling for the telltale warmth that indicated approaching criticality. A slip of the screwdriver, a moment's inattention, and he could trigger an uncontrolled nuclear reaction. His colleagues begged him to use remote controls, but Slotin insisted that only human hands possessed the sensitivity needed for such delicate work.
The implosion design was Oppenheimer's greatest gamble. Instead of simply firing one piece of uranium into another, they would surround a plutonium core with precisely timed explosive charges, compressing it to supercritical density in microseconds. 32 explosive lenses had to detonate within nanoseconds of each other. A single misfire would scatter plutonium like expensive radioactive dust.
This implosion method required mathematical precision beyond anything previously attempted in warfare. The plutonium sphere, roughly the size of a softball, had to be compressed from its normal density to nearly twice that amount in less than a microsecond. The compression had to be perfectly symmetrical. Any irregularity would cause the plutonium to squirt out sideways rather than compress uniformly. Seth Nettermeyer, the physicist who conceived the implosion method, faced ridicule from his colleagues. Nettermeyer's scheme, they called it dismissively. Even Oppenheimer initially doubted its feasibility. The mathematics alone were staggering, calculating the behavior of shock waves through different materials, predicting the exact moment when plutonium would reach critical mass, accounting for the complex interactions between high explosives and metal under extreme pressure. The team had to master hydrodynamics, metallurgy, explosives chemistry, and nuclear physics simultaneously. They were essentially trying to create a perfect spherical shock wave that would compress plutonium with the precision of a Swiss watchmaker, while unleashing forces equivalent to thousands of tons of TNT. Robert Christie, a theoretical physicist, spent months calculating the exact shape each explosive lens needed to produce the required shockwave convergence. His equations filled hundreds of pages, accounting for variables like explosive burn rates, metal density changes under pressure, and the behavior of matter at temperatures exceeding the sun's surface. A single error in his calculations could doom the entire project. The failures were spectacular and dangerous. Test after test of the implosion design resulted in asymmetrical compressions that would have produced nuclear duds. High-speed photography revealed that their explosive lenses created shock waves as irregular as ocean waves hitting a rocky shore. The plutonium, instead of compressing into a perfect sphere, was being squeezed into grotesque, twisted shapes that would never sustain a chain reaction. George Kistiakowsky, the Ukrainian-born explosives expert, nearly quit in frustration. His team went through hundreds of iterations, adjusting the shape of explosive charges by millimeters, changing the composition of materials, timing detonators with Swiss watch precision. Each failure brought them closer to the horrible possibility that they might never achieve the perfect sphere of compression needed. The explosive lenses themselves were works of art and engineering madness. Each lens consisted of two different types of high explosives, fast-burning and slow-burning, shaped and arranged so their detonation would focus the shockwave like an optical lens focuses light. The fast explosive formed the outer layer, the slow explosive the inner. When detonated simultaneously, the different burn rates would theoretically create a converging spherical shockwave. But theory and reality proved devastatingly different. The first test explosions produced shockwaves that looked like crumpled paper rather than perfect spheres. X-ray photography showed the plutonium core being compressed into shapes resembling squashed fruit or twisted metal. Kistiakowsky's team had to redesign each lens dozens of times, testing different explosive compositions, adjusting the geometry by fractions of a millimeter. The precision required was almost beyond human capability. The 32 explosive lenses had to be manufactured to tolerances measured in thousandths of an inch.
The electrical detonators had to fire within nanoseconds of each other, a timing precision that required developing new electrical systems. A delay of even a few billionths of a second would cause the compression to fail. Meanwhile, the dangers were multiplying. Plutonium dust contaminated laboratory surfaces, and scientists unknowingly inhaled particles that would remain radioactive in their lungs for decades. The beryllium used in the neutron initiators was so toxic that workers handling it developed chronic beryllium poisoning, their lungs scarring from exposure to the metal. Harry Daghlian, a young physicist, was working alone one evening in August 1945 when he accidentally dropped a tungsten carbide brick onto a plutonium assembly. The system immediately went critical, bathing him in a lethal dose of radiation. He died 25 days later, his body destroyed by radiation sickness, becoming the Manhattan Project's first fatality from accidental criticality. The uranium bomb, Little Boy, was never fully tested. They simply didn't have enough uranium-235 to waste on a test. The entire U.S. production of weapons-grade uranium from 1943 to 1945 was barely enough for one bomb. Oppenheimer and his team were essentially gambling with Hiroshima, hoping their calculations were correct. The margin for error was virtually non-existent. The gun type designed for Little Boy seemed deceptively simple. Fire one piece of uranium-235 into another at high velocity, creating a supercritical mass. But even this simple design required precise calculations about neutron multiplication, timing, and the behavior of uranium under extreme conditions. If the uranium pieces came together too slowly, the chain reaction would begin prematurely, reducing the explosion's power. If they came together too quickly, the weapon might not achieve maximum efficiency. Meanwhile, plutonium proved far more temperamental than anyone anticipated. Unlike uranium-235, which could relatively easily be fashioned into a gun-type weapon, plutonium spontaneously fissioned too quickly. Fire one piece into another, and the reaction would begin before achieving maximum compression, resulting in a fizzle that would scatter radioactive material but produce minimal explosive yield. This discovery, made less than a year before the planned use of atomic weapons, forced a complete redesign of the plutonium bomb. The implosion method was the only viable alternative, but it was infinitely more complex and had never been successfully tested. The entire future of the atomic bomb project hung on Kistiakovsky's ability to perfect the explosive lenses. Chapter 4. The Moment of Truth. Trinity Test. July 16, 1945, 5:29 a.m., Alamogordo, New Mexico. The night before the test, Oppenheimer barely slept. He wandered the desert camp, chain-smoking and reciting poetry to himself. The weather was terrible, thunderstorms and high winds that threatened to postpone the test indefinitely. Military officials worried that radioactive fallout might scatter across populated areas if the wind patterns shifted. At 4 a.m., the final weather report arrived. The storms were clearing, but barely. The test would proceed as scheduled. Oppenheimer stood 20 miles from ground zero, his face pressed against dark glass, waiting for mankind's first glimpse of artificial sun. Around him, the world's greatest scientists crouched in bunkers and trenches, their faces smeared with sunscreen to protect themselves against the anticipated flash. The bomb itself, nicknamed the Gadget, sat atop a 100-foot steel tower, its plutonium core surrounded by the explosive lenses that had consumed 3 years of desperate experimentation. Inside the device, a beryllium-polonium neutron initiator waited to flood the plutonium with neutrons at the precise moment of maximum compression. The timing had to be perfect. Too early, and the chain reaction would begin before optimal compression. Too late, and the plutonium would begin to expand, reducing the explosion's efficiency. The countdown echoed across the desert. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. The explosion defied every expectation. The flash was visible 180 miles away, brighter than the sun, bright enough to blind observers who forgot to look away.
The light lasted for several seconds, illuminating the desert like midday. Then came the heat wave, felt 20 miles from the blast site, followed by the sound, a rolling, thunderous roar that seemed to come from the Earth itself. The mushroom cloud rose 8 miles into the atmosphere, a pillar of fire and radioactive debris that would change the world forever. The steel tower holding the bomb was completely vaporized. The desert sand beneath the explosion was fused into a new mineral, trinitinite, a greenish glass created at temperatures exceeding the sun's surface. But the most profound effect was on the men who witnessed it. Enrico Fermi, one of the world's leading physicists, tried to maintain scientific objectivity by dropping pieces of paper to measure the blast's shockwave. The paper fluttered several feet, indicating an explosion equivalent to 10,000 tons of TNT. His calculation was remarkably accurate. The actual yield was 21,000 tons. But in that moment of triumph, Oppenheimer felt only horror. He later described his thoughts. A few people laughed, a few people cried, most people were silent. I remembered the line from the Hindu scripture, the Bhagavad Gita. Now I am become death, destroyer of worlds. I suppose we all thought that, one way or another. The test had succeeded beyond their wildest calculations. Every explosive lens had fired perfectly. The plutonium core had compressed to exactly the predicted density. The neutron initiator had functioned flawlessly. The chain reaction had proceeded with terrifying efficiency. In less than a microsecond, matter had been converted to energy according to Einstein's equation E equals mc squared, releasing the power of stars upon the Earth.
Kenneth Bainbridge, the test director, approached Oppenheimer immediately after the explosion. "Now we're all sons of bitches," he said simply. The words captured what many felt, that they had crossed a threshold from which humanity could never return. Chapter 5. The Weight of Success. The successful Trinity test proved that the implosion design worked perfectly. Every calculation, every precisely timed detonation, every microscopic detail had functioned as intended. The yield was equivalent to 21,000 tons of TNT, more than the explosive power of all bombs dropped in World War II combined. But this technical triumph brought no celebration for Oppenheimer and his team. The scientists at Los Alamos had spent 3 years in isolation, working 18-hour days, living in primitive conditions, all united by the desperate belief that they were racing against Nazi Germany to develop atomic weapons. But by July 1945, Germany had been defeated for 2 months. The original justification for the Manhattan Project had vanished, yet the bombs they created were about to be used anyway. 3 weeks after Trinity, on August 6, 1945, Little Boy obliterated Hiroshima and Nagasaki. The uranium bomb, which had never been tested because fissile material was too precious to waste on experiments, functioned exactly as predicted. The explosion, equal to 15,000 tons of TNT, destroyed 5 square miles of the city center and killed approximately 80,000 people instantly. The Hiroshima bomb was dropped without warning, detonating 1,900 feet above the city to maximize its destructive radius. The hypocenter reached temperatures of millions of degrees, hotter than the sun's surface. People within half a mile of the explosion were vaporized instantly, their shadows burned permanently into concrete and stone. Those further away suffered horrific burns from thermal radiation, their skin peeling away in sheets. 3 days later, on August 9th, Fat Man, based on the Trinity implosion design, destroyed Nagasaki. This plutonium bomb was even more powerful than Little Boy, with a yield of 21,000 tons of TNT. The weapons Oppenheimer had spent 3 years perfecting killed over 200,000 people in less than a week. The reports from Japan were devastating. Survivors described a new kind of hell, people walking like ghosts, their skin hanging in tatters, begging for water that would never come. Children's lunchboxes were found with the rice turned to charcoal, their owners vaporized. The lucky ones died quickly.
The unlucky suffered for weeks from radiation sickness, their hair falling out, their blood failing to clot, their immune systems destroyed by gamma rays. But perhaps most disturbing to Oppenheimer was the realization that atomic weapons worked exactly as his team had designed them. There were no technical failures, no merciful malfunctions. The bombs killed efficiently and completely, leaving behind a radioactive wasteland that would remain dangerous for decades. The moral weight crushed him. Oppenheimer had entered the project believing that defeating Nazi Germany justified any means. He had convinced himself that developing atomic weapons was a race against Hitler, that failure would mean Nazi domination of the world. But Germany had surrendered months before the bombs were used. The weapons he created to save democracy were instead used to end a war that conventional invasion might have concluded. Military planners estimated that Operation Downfall, the planned invasion of Japan, would cost between 250,000 and 1 million American lives, plus millions of Japanese casualties. From this perspective, atomic weapons saved lives by ending the war quickly. But Oppenheimer struggled with the knowledge that his bombs had introduced a new form of warfare that could potentially end human civilization. Chapter 6: The Reckoning. After Hiroshima and Nagasaki, Oppenheimer became the most famous scientist in America, and the most tormented. His gaunt face appeared on magazine covers worldwide, portrayed as both a hero who had ended the war and a villain who had unleashed ultimate destruction. Time magazine called him the man who brought the world to the threshold of doomsday. But fame brought no peace. Oppenheimer testified before Congress, advocating for international control of atomic weapons. He proposed that the United States share atomic secrets with the Soviet Union and establish a global authority to prevent nuclear war. His colleagues and government officials were appalled. How could the man who created America's ultimate weapon now argue for giving it away? His testimony was passionate and desperate. The atomic bomb is not just another weapon. It represents a qualitative change in the nature of warfare. We have crossed a threshold. If we continue down this path, we will create weapons that can destroy not just cities, but entire civilizations. But his warnings were ignored. The Cold War was beginning, and America's nuclear monopoly was seen as crucial to national security. Oppenheimer found himself increasingly isolated, his moral objections dismissed as naive idealism. The breaking point came with the hydrogen bomb. Edward Teller, the brilliant Hungarian physicist who had worked with Oppenheimer at Los Alamos, proposed developing a weapon 1,000 times more powerful than the bombs that destroyed Japan. The hydrogen bomb would use nuclear fusion rather than fission, potentially creating explosions measured in megatons rather than kilotons. Oppenheimer opposed the hydrogen bomb's development with every fiber of his being. He argued that such weapons had no conceivable military purpose. They were too powerful to use tactically, too destructive to serve any rational strategic goal. The hydrogen bomb is an evil thing, he told the Atomic Energy Commission. It is a weapon of genocide. His opposition was both moral and technical. The hydrogen bomb required precise engineering challenges that made the atomic bomb seem simple by comparison. Fusion reactions required temperatures of millions of degrees to sustain, meaning the bomb would need an atomic bomb as a trigger. The technical hurdles were enormous, the costs astronomical, and the ultimate weapon would be too powerful for any conceivable military use.
But Teller and other scientists argued that the Soviet Union was already developing hydrogen weapons. America could not afford to fall behind in the nuclear arms race. National security required pushing the boundaries of destructive capability, regardless of moral qualms. The debate split the scientific community. Many Manhattan Project veterans supported Oppenheimer's position, believing that atomic weapons were already powerful enough to deter any enemy. Others, particularly younger scientists who had not witnessed Hiroshima and Nagasaki, argued that America needed the most advanced weapons possible. His former colleagues turned against him. Edward Teller, who had once been his friend and collaborator, testified that Oppenheimer's moral objections endangered American security. Teller claimed that Oppenheimer's opposition to the hydrogen bomb was motivated by communist sympathies rather than genuine ethical concerns. The accusation was devastating. Oppenheimer had indeed been associated with communist organizations in the 1930s, motivated by concern for social justice and opposition to fascism. His wife, brother, and several close friends had been Communist Party members, but his loyalty to America had never been questioned during the Manhattan Project. Now, in the paranoid atmosphere of McCarthyism, his past associations became grounds for suspicion. In 1954, Oppenheimer's security clearance was revoked in a hearing that destroyed his public career. The Atomic Energy Commission concluded that while he was not a security risk, his moral objections to nuclear weapons made him unsuitable for classified work. The man who had successfully managed the most complex scientific project in history, who had solved seemingly impossible physics problems, who had literally harnessed the power of stars, found himself branded as unreliable by the very government he had served. The hearing was a kangaroo court. Oppenheimer was denied access to classified documents needed for his defense, while his accusers were given full access to FBI surveillance files. The proceedings were dominated by Cold War hysteria and personal vendettas. Scientists who testified on Oppenheimer's behalf found their own careers threatened. Epilogue: The Prometheus of Los Alamos. Oppenheimer spent his final years as director of the Institute for Advanced Study at Princeton, far from weapons research, far from government laboratories, far from the nuclear establishment he had helped create. The man who had once commanded the loyalty of Nobel Prize winners and managed budgets of hundreds of millions of dollars now found himself effectively exiled from American science policy. But exile brought a different kind of productivity. Free from security restrictions and government oversight, Oppenheimer returned to his first love, pure physics and philosophy. He continued teaching, reading poetry, studying Eastern philosophy, trying to understand what he had unleashed upon the world. He became a popular lecturer, speaking to packed auditoriums about the relationship between science and society. His lectures were haunting. The physicist has known sin, and this is a knowledge which he cannot lose, he said. He spoke about the burden of knowledge, the responsibility of scientists to consider the consequences of their discoveries. He argued that the atomic bomb had changed not just warfare, but the fundamental relationship between knowledge and power. He wrestled with the paradox of his legacy. The Manhattan Project had represented the greatest mobilization of scientific talent in history, proven that theoretical physics could be transformed into practical applications with unprecedented speed and efficiency. The project had accelerated scientific research by decades, leading to advances in nuclear medicine, power generation. But it had also demonstrated science's capacity for destruction on a scale previously unimaginable. The nuclear weapons he had created continued to multiply. By the 1960s, the United States and Soviet Union possessed thousands of hydrogen bombs, each far more powerful than the weapons that destroyed Hiroshima and Nagasaki. The arms race he had tried to prevent had become the defining feature of international relations. The doctrine of mutually assured destruction meant that human civilization now lived under the constant threat of annihilation, a threat made possible by his scientific achievements. Yet Oppenheimer also saw reasons for hope. The same nuclear physics that enabled weapons also powered submarines, generated electricity, and produced medical isotopes that saved lives.
In space exploration, nuclear medicine could now treat cancer, sterilize medical equipment, and trace biological processes in living organisms. Nuclear power offered the possibility of clean, abundant energy that could lift billions out of poverty. In 1965, President Lyndon Johnson awarded Oppenheimer the Enrico Fermi Award, a gesture of rehabilitation that came too late to repair his reputation, but acknowledged his contributions to science. The ceremony was awkward. Many of the officials who had destroyed his career were present to celebrate his achievements. Oppenheimer accepted the award quietly, without bitterness, using the occasion to speak once more about the responsibility of scientists in the nuclear age. He said, "We know too much for one man to know much. We are not only scientists, we are men. And as men, we must take responsibility for what we have learned and what we have made possible." He died in 1967 of throat cancer, possibly caused by his decades of chain smoking, possibly by radiation exposure during the Manhattan Project. He took with him the unique burden of being the man who had shown humanity both its greatest intellectual achievement and its capacity for ultimate destruction. The weapons he created would define the next century of human conflict, ensuring that future wars would be fought under the shadow of annihilation. Nuclear proliferation continued long after his death, with more nations acquiring atomic weapons despite his warnings about their dangers. But his scientific legacy extended far beyond weapons. The methods developed at Los Alamos, bringing together diverse specialists, coordinating theoretical and experimental work, maintaining security while encouraging innovation, became the model for every major scientific project that followed. The space program, the Human Genome Project, the development of computers and the internet all borrowed organizational techniques pioneered during the Manhattan Project. The bomb worked exactly as Oppenheimer designed it. The physics was flawless, the engineering perfect, the execution precise. That success haunted him until his final day, but it also represented one of the greatest intellectual achievements in human history. His legacy remains as complex as the man himself. Brilliant physicist, effective administrator, moral philosopher, and reluctant father of the atomic age. He had sought to harness the fundamental forces of the universe and succeeded beyond his wildest imagination and his worst fears. The atomic bomb was perhaps humanity's greatest technical achievement and its most terrible mistake. And it all began with one man's desperate attempt to save the world by learning to destroy it. In the end, Oppenheimer's story is not just about nuclear weapons. It's about the awesome responsibility that comes with knowledge and the price we pay for pushing the boundaries of what is possible. Today, more than 13,000 nuclear weapons exist worldwide, many hundreds of times more powerful than the bombs that destroyed Hiroshima and Nagasaki. Oppenheimer's warnings about the dangers of nuclear proliferation have proven prophetic as more nations acquire these weapons and non-state actors seek to obtain nuclear materials. Yet his vision of international cooperation and arms control continues to inspire efforts to reduce the nuclear threat. Treaties limiting nuclear weapons, international monitoring systems, and diplomatic efforts to prevent proliferation reflect his belief that humanity must learn to control the forces it has unleashed. The question Oppenheimer posed in 1945 remains unanswered. Can humanity possess the ultimate power of destruction without eventually using it? His life's work gave us that power. Whether we prove wise enough to control it remains the defining challenge of our time.